Let's say you live in the city and you're giving somebody directions to your house. So they are here, your house is over here. You say, hey, why don't you go about 3 miles east and then go 4 miles north? We'll pretend that's proportional. 4 miles north, and then you'll arrive at my house, right? How far are they from where they started? I think we could start to see that in this situation, they, if you calculated this distance, you'd recognize that, hey, Mr. J, you're making a triangle over there. Basically, I could just use some Pythagorean theorem action, a squared, b squared, c squared, to find out that this would be 5 miles away, like if you were able to go straight there. Okay, let's say you had a plane. There's my plane. That's a plane. Don't judge me. And it was going 30 miles per hour east. Wow, what's more realistic? That's like 300 miles per hour east. But encountered a wind that was like 400 miles per hour north. Okay, that's not very realistic, but go with me on this. If I want to know, hey, what's the actual speed that that plane is going? Because it's going to end up going this way. It's getting pushed off course. We have a triangle again, and you're going to find that that actual speed is going to end up being 500 miles per hour. Likewise, if we have a box and there's a force being applied to it of, let's say, 30 newtons this way, and oh, by the way, there's a force being applied to it upward, somebody's trying to lift it with 40 newtons that way, and I want to say, hey, how much net force is actually on that box? How do we combine the effect of both of those? We'll take a guess. I'm going to cut and paste this guy over here, and I get the same triangle we've been making this whole time. And 30 newtons and 40 newtons at a right angle there gives me 50 newtons in that way. Basically, any measurement you can represent with magnitude and direction. That's to say, anything that is a vector, you can do, what we're doing is basically vector addition, right? It behaves just like the geometry would have you believe, and just like the geometry would work. And in fact, not just Pythagorean theorem, which comes in super handy, but other things about triangles too. If you knew this angle, right? The same applies for cosine of that angle is, let's see, adjacent over hypotenuse. So that would mean adjacent was 300 miles per hour over 500 miles per hour. Same thing for sine of that angle, opposite over hypotenuse, right? So 400 over 500. And in fact, in general, if you want, let's say, if this were, let's scoot this over, if this were some force at an angle, and say, you know what, I have a force at this angle, but I want to know, like, how far is it pulling sideways? How much is it pulling up? And I want to break that into what we call components, specifically x and y components. Well, all right, we can do some trig to do that because vector addition lets us do that. Fx is going to be hypotenuse, the F, the original force, times the cosine of theta. Fy is going to be the hypotenuse, F, times the sine of theta. That proportionality holds. Hooray for Euclid and geometry and all that stuff that came before us. This is where that actually applies. Why did you have to learn that in math class? This is why. These relationships are going to be pretty powerful for us as we try to have a force at an angle and need to break that into components that are more handy, more useful for us. So basically, this force here at an angle is equivalent to these other two that are in x and a y direction. And you can replace it with either one, and you haven't changed the scenario. We're just kind of looking at it from a different perspective.